and we'll just fire away. And if it's something where like we want to review the entire topic, we can review that, spend some time looking at that specific topic from the practice exam, or if it's talk about how to handle the question, or kind of whatevs, we can do that. But that's my plan here for the next 2 days, is to really just spend some time kind of looking at where we feel uncertain or where we're a little soft or whatever, and just kind of shoring up those areas the best we can. Let's all start on the same section so everybody's not like shuffling through like 4 separate packets. Probably makes the most sense. I find typically the free response questions tend to be the most difficult for students. So let's start on the no calculator free response questions. I think are probably the ones that tend to be the most difficult for students. All right. Oh my goodness. Get this turned on. You can't see diddly poo right now. Okay. Is everyone looking at the same question right now? Okay. So, I now open the floor to you guys, and we can start kind of wherever you'd like inside of this section. So you can just fire away. Lucas. Number 6. All right. It says for 0 to 6 seconds, a screensaver on a computer screen shows 2 circles that start as dots and expand outward. At an instant that the first circle has radius 9 centimeters, the radius is increasing at a rate of 3/2 centimeters per second. Find the rate at which the area of the circle is changing at that instant. Indicate the unit of measure. When you read this question, what type of question is this? This is a related rates question, right? Thank you. We have so many of these. Violet, Paulo, and Jack Karasak. You guys can grab your pass. Yeah. You're welcome. Oh, shit. So, for related rate problem, the first thing I'd want to do is start by labeling the given information with a descriptive with a description here, or with descriptive variable name. So the first sentence says, at the instant that the first circle has radius of 9, the radius is increasing at a rate of, so whenever I see rate, that's my derivative. And we're told that's when the radius is 9. That this is 3 over 2. Everybody's okay there. Now it's asking to find the rate in which the area of the circle is changing. So the previous information gave me information about the circle's radius. So the equation for area that I want to write needs to be in terms of just the radius. Well, that's fine, because the area formula for a circle is just pi r squared. Do they expect you to remember that? Yes. Would they expect you to remember not a basic geometry or trigonometry formula? No, it probably wouldn't have a trapezoid or something in there that's kind of kooky without them telling you. Or the area or the volume of like a cone, they would probably not put in there without telling you. But like area of a circle, area of a triangle, square, rectangle, volume of a cube, or volume of a rectangular solid, those are things that they would probably expect you to remember the formulas on your own. But they're like the easiest of the easies. All right. So we have this. Now we'll take the derivative of both sides. When I do that, the derivative of a with respect to t becomes dA dt. Pi is a constant, so I ignore it. The derivative of r squared is going to be 2r and then dr dt. So we are looking for dA dt when the radius is 9. So all we need to do is plug stuff in now, right? So that's going to give me 27 pi. And it says indicate units of measure. So this is an area. So the unit should be centimeters squared. And because it's a rate, it's dt, it's per time. The time unit here is per second. So centimeters squared per second. So areas are in centimeters squared because the linear unit was in centimeters. And the time rate is just in seconds because that's the rate that we've given earlier. That part should be fairly easy, right? That's all kind of a slam dunker of a question as far as a related rates problem goes. Didn't have to do any change of variable. Like it's basically, do you remember the area formula for a circle and can you take the derivative of it? All right. It says the radius of the first circle is modeled by the function w of t equals yada, 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 where w of t is measured in seconds, or in centimeters, and t is measured in seconds. At what time t is the radius of the circle increasing at a rate of 3 centimeters per second? So basically we're asking to solve for this, right? So the derivative, or the rate in which the radius is changing, if this is the model for the radius, the rate is just going to be that. So all I need to do is take the derivative of w of t. What derivative rule am I going to have to use to do that? That is a chain rule. Notice because I have a function inside the exponent of that exponential. So the derivative of 12 is 0. The derivative of 12 e to the negative 0.5t, well, I can ignore the 12. The derivative of e to the x is just e to the x. And then the derivative of that exponent is just going to be negative 0.5. So I'm going to have 6e to the negative 0.5t is equal to 3. So to solve this, then, we'll divide both sides by 6 to get the exponential piece by itself. We'll do the natural log of both sides to cancel out the base of the exponential. And then multiply both sides by negative 2 to get rid of the negative 0.5 coefficient. And this would be in seconds. Do we feel okay on what we did there? Notice this was not in any way related to part A. So even if you, like, I don't remember how to do a related rates problem, I'm punting on part A. Part B was just like find the derivative and solve for a value, like super easy. You just have to like read the question, sort through what you have to do. Usually the what of what you have to do is not that difficult. Figuring out what to do or how to do it is usually the hard part, but the actual execution tends not to be that complicated. All right, part C, it says a model for the radius of the second circle is given by the function f from 0 to 6, where f of t is measured in centimeters and t in seconds. The rate of change of the radius of the second circle is given by f prime of t equals t squared minus 4t plus 4. Based on this model, how many centimeters does the radius of the circle increase from time 0 to 3? So what we want to do is when I hear this, I hear this as like an accumulation problem. When I think of accumulation, what calculus operation am I thinking about? The integral. So I'm going to be integrating from 0 to 3 the rate at which the radius is changing. Everybody's okay with that? So that'll tell me how much total the radius changed over that time. So again, that's a very easy integral to do. The antiderivative of t squared is t cubed over 3. The antiderivative of negative 4t is negative 4t squared over 2. And the derivative of 4 is just 4t. And then they were very nice because they gave us 0 on the other side. And since everything has a t in it, just everything just zeroes out there. And at this point, technically, I could be done, right? I don't need to simplify this any further, although it's a pretty easy simplification to make. So I have 9 minus 9 times 2, that's 18, plus 12, that gives me 3 centimeters total. Again, the numbers there were nice. They did us a solid because, again, no calculator, so the numbers shouldn't be gross. Does that feel okay, Lucas?
Yeah.
Good. Everyone else, any questions on this? Any questions on the concepts that were involved? Again, I think the concepts here are things that we are definitively good at, right? The things that we're asked to do in this question. It's just a matter of, can you slow down your thinking, read the question well enough, and go, okay, that's all I need to do is like take the derivative, set it equal to this, and solve. Or integrate this, from here to here. Like, for the most part, this is what these free response questions look like. When you know what to do, they should feel pretty easy. The hard part is reading the question and understanding what to do and being confident that you're selecting the right thing to do. And if things look like it's starting to get ridiculous, you're probably doing too much. You've misread something in the question. They're typically not spectacularly tricky. Okay? So try to do the obvious thing, is my typical advice, particularly if you've prepared, if you've been studying. Trust your instincts. Do the obvious thing. Was that good, what I talked through when I was like reading this, and like, what did I see? Where was I getting my clues? What was I, like when I hear this phrasing, what am I thinking of? What does that tell me to do? I'm trying to do that a lot, because at this point you guys know the mechanics, I think, pretty well. Just a question of like, can you read the question and know which thing to do, right? If you knew what to do, typically things go really well. And even when I think back to the tests we took in class, that was most of the questions you guys would come up with. It's just like trying to figure out what to do. And like once you figured that out, getting it done you were usually pretty good at it. It was just a question of like, can I get past, what do I need to do here? So that's what I'm really trying to focus on while we're going through this, is knowing what to do. Okay, next up, who's next? Others from this section, or from this block of questions. Ryan. For sure. All right. 5 says, let R be the region in the first quadrant enclosed by the graph of square root cosine x, the graph of e to the x, and the vertical line pi over 2 as shown in the figure above. So first thing I would do before I do anything more is make sure I figured out which is which, right? So like, that's F, that's G, and this vertical line is obviously the vertical line, right? How can I tell which one is which? Well, I know what an exponential function looks like, right? That it should be concave up the whole time. That's what I'm seeing. Cosine starts at 0, 1, and then like, so that looks good to me. Even though the square root's over top of it, that's not going to change where it starts, because if it starts at 0, 1, if I square root 1, it's still at 0, 1. And then it decreases after that. If I take the square root of a number, it's just going to make it, a number less than 1. If I square root it, it's still going to be less than 1. So I'm good. I feel good about that. All right. It says, write but do not evaluate an integral expression that gives the area of R. So if I think about it, I want, this area, right? Now I'm not going to do that in all one chunk. What I would do is I would do the area of F, or the area under F, and then subtract out, the area under G, and then subtract out the area under F. Sound good with that? So R is going to be the integral from, we're starting at 0, and we're ending at pi over 2, of the function on top, that's g of x, and then we'll subtract out the area under f of x over the same interval. And I'm done. You don't have to do anything more than that. It says write an expression, do not evaluate. I don't have to write the functions in there. I can just call them f and g, save myself, extra 20 seconds of writing, or the possibility of me doing something dumb and copying the wrong symbol, or not writing something to somebody the grader's liking. I'm just going to write f and g. Alternatively, if you use an absolute value and you write it this way, the order doesn't matter. So if you get confused and you're like, which one's on top, which one's on bottom, just stick them together in the same integral with an absolute value around it, and it will not matter. That's a nice hack for this kind of question. Even if it's like a calculator question where you're going to type in your calculator, the calculator handles absolute value just fine, right? Now, for you doing it by hand, it stinks. You don't want to do that. But in this setting where you don't have to do the actual integral, use the absolute value if you're unsure. If you're like, I don't remember which one should be on top and which one, I know I subtract the two of them somehow, just put an absolute value around it and it's fine. But it has to be around the two things inside the integral. It can't be around I don't know. I think it should be. Might still be okay if you put the absolute value around. I'd have to think about it for a minute. If you put the absolute value around the entire integral, might still be okay. I'd have to think about that for a moment, though. In this case, it would. I know it would be for this case. In general, though, is what I'm worried about. Anyway, Ryan, does that feel good? And again, that's a nice pickup, like a nice little hack. Like, I can use that absolute value if I'm unsure. Okay, it says find the volume of the solid generated when R is revolved around the x-axis. So if I'm going to go ahead and erase all this stuff, so I'm going to be going around the x-axis, right? So this is going to be the center of my figure. So the first thing I'm going to look for on a volume of rotation problem is deciding whether I'm going to be using washers or discs, because there are no shells that are necessary on this exam. Now you could use a shell, that's fine, but there'll be no problem where it's more advantageous to use a shell than it is to use something else. So if you're uncomfortable with the shell piece, or if you're reviewing, I wouldn't even bother reviewing it. Everything can be done easily with disc and washer. No advantage to using a shell. So what am I looking for in deciding whether to use a shell or, a disc or a washer? So I'm looking at the area, and I'm looking to see if that area touches the axis of rotation, which it does not. Right? There's a part of it at least where the area is not touching the axis of rotation. That's telling me it's a disc. Everybody okay with how I identified the disc versus a washer? if this was just, if there was no lower function, if it was like this the whole way, where the area is touching the axis of rotation the entire time. Yeah, go ahead. Then I would use a disk. All right. So to do a washer, we have to remember the formula. Right? So it's the radius of the outer squared minus the area of minus the inner squared dx. And you have to stick that pi out front because it's really just pi r squared minus pi r squared, but we'll just factor the pi out front. You could put it in both places, that's fine. Okay, so if I draw my picture, so I'll pick like an arbitrary x value. So this is like my R inner, and that's like my R outer. So my R inner is just going to be that y coordinate, which is the f of x. And the R outer is just going to be this y coordinate, which is just g of x. So we're going from 0 to pi over 2 of g of x squared. Just going to write it here, minus f of x squared dx. And I guess it should go without speaking why I'm doing this with respect to x, right? When the axis of rotation is a horizontal, it's a dx. We're using x's for disks and washers. The axis of rotation is vertical. We're doing dy's for disks and washers. All right. So g of x was the square root of cosine x squared, and f of x was e to the x squared. And now I would, oh my goodness, I have those in the wrong spot. Sorry, g was e to the x. I was like, that's going to give me a negative value. I started seeing it. That's not right. There we go. Now I'm going to simplify this before I get started integrating, because I know the squared is going to cancel out the square root. And e to the x squared, I can just write e to the 2x. And I'm really going to think about the, oops, still have my pi. And I'm really going to think about this as two separate integrals. It's probably the easiest way to conceptualize things. So for the first one, the only problem is that 2x, right? So I'm going to need to do a u sub here, because I noticed that I have like a composition of two functions. Whenever I'm trying to integrate a composition of two functions, typically the u sub is going to be the way to go. So again, the 2x would be my u. I take the derivative of both sides and then solve for dx, and I get du over 2. And is it worth doing? Maybe. So I'm going to reset the bounds as well. Does that all look okay so far? Now the integral of cosine, that's very easy, right? That's just a straight antiderivative formula. What is the integral of cosine? It's sine, right? Because if I take the derivative of sine, I get cosine. Again, like those things have to be cold memorized. There's no ifs, ands, or buts about it. Those antiderivative formulas, you have to have cold memorized, stone cold. And now I can just finish my plugging in now that I've done my antiderivatives. And I suspect that if you get this far, you're done. Oops, that's a plus though. Oh my gosh. Over 2. Because I have that still. All right. So when I do that, this is going to be, again, you could probably stop here. I would suspect that would be fine. But, you know, sine of 1/2 is 1. Sine of 0 is 0. So pi times e to the pi over 2 minus 3 over 2 or something like that. Again, there's, you know, you could pull the 1/2 out, I guess, also. It's probably the prettiest way to write it. But style doesn't count, right? I suspect at this point, you would be okay and not evaluating all the trig stuff. I don't think matters. Now I'll say this, just coming to thinking about it. When I did training for this course, we talked about like how the graders grade things. My recommendation to you is don't circle answers. So if you think you're done, don't circle the final answer. Let them find it, because if you have the correct answer somewhere and then you go on past it, make a mistake, if you haven't announced, like, this is my final answer, it's on them to choose your final answer. And I think more often than not, you're going to get, you know, you'll get the marks because it's on there, even if afterwards you did something to mess it up. So my suggestion to you on this is don't circle final answers on the free responses. Just do your work. And when you're done, just go to the next question. Don't circle anything, like announce like this is the answer that you're looking for. Let the grader find it. Now try to be organized and like make that easy for them. But if like, this expression is equivalent and you have it, and you continue on and do something else and you mess it up, I think if you don't circle it, you'll probably end up with full marks. So just came to me while we were talking. So, all right. And then part C says region R is the base of a solid whose cross sections perpendicular to the x-axis are semicircles with diameters in the xy plane. Write, but do not evaluate, an integral expression that gives the volume of this solid. So this is that other type of volume problem where there's no rotation going on, right? So remember that the volume is just going to be the integral of some area function, right? Now, because we're told we're perpendicular to the x-axis, that's telling us it's a dx question. And because we're told semicircles, I know that semicircle is half of a circle. So I'm going to do that. And now all that I need is to come up with an expression for r of x, the radius of those semicircles in terms of an x. Does that feel good to everybody? And I suspect this is a point already. Like 1 point of credit for this question is enough if you've given them this without even finding the specific r of x or the value. So to do this now, I'm going to go back to my picture. I'm going to erase all my marks from before so I have a clean picture. So the radius function that I'm looking for is that, right? That would be my r of x. Do you guys buy that? Oh no, that's like a, I'm sorry. That's like a d of x. That's a diameter for the semicircle. So that should be then g of x minus f of x. So the radius function should just be half of that. Everybody feel okay there? I suspect that's your second point on that question, would be correctly coming up with an expression for that radius function. Maybe you need the bounds of integration there also somewhere, but and that should be sufficient. Ooh, did I screw that up on my key, didn't I? I think I probably do need an over 2 there. Yep. Bother. I'll fix that and repost. How do you guys feel on that? These volume problems? We did a lot of practice here. We did a whole test basically just on doing these kind of volume problems. My suggestion to you as you go, discs and washers is all you need to review, and then this non-rotational volume situation, but they are all the same. They are an integral of the area function. You just have to write an expression for the area function in terms of a single variable. And then in this case, where you don't have to evaluate, all you got to do is write it in and fill it in. Notice that I didn't bother, again, to write what f of x and g of x was. I just wrote the F and the G because it felt like just one more opportunity for me to like have some messy handwriting or like forget a square root on top of the cosine or, you know, do something dumb where I miscopied something. I'm just going to use one letter, save myself 10 seconds or like some flipping back and forth if it's a complicated expression. What do you guys think? Does that feel okay? Again, notice that like anything that was kind of complicated, you didn't actually have to find the answer for, right? The two that would have been complicated integrals, you did not have to do. So you just had to set it up and stop. Again, that's an important piece that as you're reading this, if it's like write but do not evaluate, don't start evaluating because you're going to burn a whole bunch of time trying to do something that's really difficult because you missed that direction. It's an easy place to like fall down a rabbit hole and waste 20 minutes trying to do a problem you're not supposed to be able to do by hand. Which this thing would be an ever-loving nightmare to do by hand. Mostly because of when you FOIL that thing out, you'd have a e to the x times square root cosine x, and I have no clue what I would do to try to evaluate or integrate that particular product of those two functions. That's a parts problem, maybe, but boy, that's a rough-looking parts problem that I'm not even sure will work. Doing it by parts, that might be one of those where you have to do a couple of cycles till you get the same thing and then add it back over, and it sounds really difficult to me. I don't want any part of that. What makes part A, the integral, really difficult would be integrating the square root of cosine x without another trig function in it. Again, I'm not really sure what I would do with that. Might be one of those integrals that's just intractable. So again, like make sure that if it says write but do not evaluate, that you catch that when you're reading the direction and don't start trying to do an integral that's going to be kind of impossible or beyond the scope of, you know, where you're at to be able to do, because it's a real time consuming oopsie to miss that direction. Should we move on to another section of problems? What do you guys think? We can always circle back on the next day if you're looking through things and you want to go back and talk about something else from here. Should we go to the other free response questions? Let's do maybe try to do the free responses today and tackle the multiple choices next time or something. That feels probably pretty good. All right, so these are the calculator-based ones. And there's just two of them, notice. So again, you'd have 30 minutes to do these two questions. Before you would have had an hour to do 4 with no calculator. As far as like the free response questions go, I think that the calculator-based ones are easier if you're like shaky on your on like your algebra, because the calculator is going to do like all the difficult part, all the algebraic parts, all the computate, like the symbol pushing. Your job is just to set up. If you're good at setup, this is a place to sock some points away. These should be pretty easy because the calculator, again, is going to do most of the work for you. You just got to be able to set it up. So if we look at the first question, this is a like velocity, acceleration, position question. So the key there is remembering that, you know, like velocity is the derivative of position and acceleration is the derivative of velocity or the second derivative of position, however you want to think about it. So here you're told a particle is moving along the x-axis, so its velocity is given by the function v of t equals some terrible looking thing. At time t equals 0, the initial position of the particle is x equals 7. Find the acceleration of the particle at time t equals 5. So the acceleration at time 5.1 is just the derivative of velocity evaluated at 5.1. And this is as much as I'm writing down other than my final answer, because the rest of this is all getting done in the calculator. So I would go into the y equals, and I would type in my function as it looks on my sheet of paper for the velocity. I like doing it in the y equals because on a problem like this that's got multiple parts, I'm probably going to end up reusing this problem to do something else. So I wouldn't have to type this in a second time. I can just call y1 every time I need it, and it saves me some time punching things into a calculator. Plus, it's easy for me to look at the whole thing right here. Sometimes on your calculator screen when you're typing it inside of like the derivative thing, it's hard to see what's going on. Here I can clearly see that I've got everything in the right spots, and it's easy to double check. So then to do the derivative, I'm just going to press Math, scroll down to the bottom till I find n derive, put an x for dx because that's the way I wrote my function, vars, y vars, function y1, and then I'm evaluating it at 5.1. And then I'm going to type in my answer. I think 3 decimal places is kind of the standard of what they're looking for on these calculator questions. I suspect 2 would be fine also, but and then no units are given in this problem. Notice that it says the velocity is just this function. It doesn't tell us what v of t is in terms of or what t is in terms of. So I'm not writing any unit on my answer. You know, doesn't need a unit if they haven't given you any units. If this was in like meters per second and t is in seconds or something, then this would, the velocity or the acceleration would be meters per second squared, right? Or meters per second per second. Find all values of t in the interval from 0 to 2 for which the speed of the particle is 1. So this is tough because they use the term speed rather than velocity. Are those two the same thing? No. This is something I didn't hammer at you guys too hard. Those of you that are in physics know this. But what is the difference between speed and velocity? Correct. Speed is an absolute value of velocity. Velocity has a direction, has negative and positives. Speed does not. Like your car has a speedometer because when you're going in reverse, it reads it as positive 15 miles an hour if you've got it like floored in reverse. I don't know why you're going 15 miles an hour in reverse. That's crazy. Don't do that. But if you had a velocimeter, it would be negative 15 if you were going in reverse. All right. So what I'm going to do, that's what I'm writing on my sheet of paper. But the only thing I'm doing now on my calculator is the rest of this is all going to be done in my calculator. So I'm going to turn off my graph for y1. And then in y2, I'm going to graph the absolute value of y1. So I don't have to type all that junk in and over again. And then 1. And I'm going to graph this now, but I'm only going to graph it on my x's from 0 to 2 because I don't care about anything else. And that is probably fine because I can see where it's going to cross 1. So I don't have to worry about the y's there. Now I'm just going to press enter and give it a second to do its thing. And then I'm just going to find the intersection. So it looks like I have 2. So second trace, intersect command, enter, enter, and then for my guess, because there's multiple intersections, I'm gonna move it close. So I have 0.772 And then for the guess, again, I'll move closer this time. And I have 1.401. Feel good? Again, notice that like the calculator is doing most of the work for me here. If I'm good with my calculator, I'm good with my setups. These are easy, quick questions. Part C says, find the position of the particle at time t equals 4. Is the particle moving forward or moving toward the origin or away from the origin at 4? Justify your answer. My opinion, I thought that this was the most difficult question on this entire practice, or certainly the most difficult of the free response questions. So my position function is going to be equal to the position at time 0 plus the integral from like, I mean, I guess you should say this is just 4. 0 to 4 of phi of t dt. Easy to forget this. This is your constant. That's your plus c when we're integrating. But it tells us that in the problem, right? At time t equals 0, the initial position is 7. So we know that. So the rest of this I'm going to do on my calculator, at least this first part, to find the position. So I'm just going to do 7 plus, and then math, fn int 0 to 4 of that y1. So I have 6.712 or thereabout. And I wrote it as x because in the problem they give the positions as x equals, right? Because it's moving along the x-axis. So if I think about it, at time t equals 0, we're at 7. At time t equals 4, we're now backwards, 6.712. What I need to do now, though, is I need to figure out whether it's this particle is moving forward or backwards. So the question is it doing this or is it doing that? What's going to tell me that? The velocity. Yeah, so I'm going to check v of 4. Again, not doing that by hand. And again, I'm not typing it into the calculator. I'm going to use y1, which is where I type the velocity function. I'm just doing y1 of 4. Now it gives me this because I typed it in using the fraction mode. I don't love that, so I'm just going to use the decimal command. So I'll write that is 1.213, and that's greater than 0, so it's moving forward. So we're doing this one, which would be away from the origin. Since we're right of the origin and moving forward, we're going away from it, right? Notice it's saying origin, not original position. We'd be moving towards the original position, but that's not what the question asked, right? Does everybody feel okay? And I think that this justification would be enough, you know. If you wanted more, I think that like a number line would be great. You know, like I think that picture says a lot. And that's pretty sufficient, I would think, to justify your answer. I wouldn't write a whole lot for this. A picture, I think, speaks volumes about what's going on. It says, during the time interval from 0 to 4, does the particle return to its original position? Give a reason for your answer. So the original position is x equals 7, right? And we're talking about positions. So basically what I'm trying to solve is, does S of t equal 7? I think the easiest way to do that is to say, okay, well, my function for S of t was that. So on my calculator, I can just graph those two things and look for an intersection over that time interval. Now the only hitch to this is it's slow. But we don't have to graph it over a whole lot. 0 to 4. I don't care about any of the negative stuff. I just needed to see where it's crossing 7. So I'm going to go ahead and just make my window a little bit smaller so it goes a little bit quicker. The bigger your window, the longer this is going to take. But this is, I think, by far the easiest way of doing this. Now you're seeing it just putzing along. So you're going to we'll have to wait a minute, but we're going to see that it will indeed come back down and cross. The other option, you can make an intermediate value theorem argument here. I think doing this is by far the easiest. It's just a little bit time consuming. So if I were you in this sort of situation, I would set this up and let it go, and I would just start the next problem. And while this thing is going, and it's like, okay, let me do the setups on what I'm going to need to get into my calculator for the next problems. When this thing is done, I'll circle back and write out my answer here and finish the things that I set up. But this is going to take a minute. But you, at this point already, you can probably see it heading back down towards 7. I think it's going to get, well, I know I did it already. It does get there and cross, but I think that's the easiest way of handling this question. But you have to remember how to get that integral graph on your calculator. But that's a powerful tool to use, and I think like an easier argument than making an IVT argument. The IVT argument, though, would not be hard because you've already got the harder one to find. You have the value less than 7. You just need to find some value that's not 0, that's greater than 7, and you got it. I think I used 1, and I got 9 point something. So you could do that pretty easily. When you use the IVT, though, what's the one thing you have to remember to state before you start using it? Continuity. Yes. All right. We'll talk about MCQs next time.